Very warm good morning, my dear students. I am Professor Ravindra K, handling the subject on the course on EC402 Nanoelectronics. In the last class, we have discussed about the MOSFET structures and how a MOSFET could be considered as a two-dimensional electron gas system and its construction features, band diagrams, and all those things we have discussed. Today, in this class, we will discuss about the heterojunctions and in particular about the modulation doped heterojunctions. So what is a heterojunction? Heterojunction is a junction formed by two semiconductors of different band gaps and lattice constants. That I have already told you about that. The heterojunctions are formed by two dissimilar semiconductor materials, two different semiconductor materials with different band gaps and lattice constants. So lattice constants means it is some of the dimensions of the crystal structure. That is lattice constant. We will discuss it later. So heterojunctions are 2D channel for carriers at the interface. In semiconductor lasers, they provide both optical and carrier confinement. So heterojunctions which are 2D channels or two-dimensional electron gas channels in which the carrier confinement is run on one direction and the electron has a motion possible in two directions. That is why it is called two-dimensional electron motion. In a heterojunction, if the dopant of the two sides are of the same type, then it is called isotype heterojunction. Otherwise, if the dopants of the two sides are different type, it is anisotype heterojunction. The most studied heterostructures is the one formed by N-type aluminum gallium arsenide, which is almost intrinsic in nature, of course lightly doped usually, with a P-type gallium arsenide. Usually, most of the nano electronic devices which are formed or which are manufactured, which are fabricated with N-type aluminum gallium arsenide material which is lightly doped, which is almost intrinsic in nature, with a P-type gallium arsenide. And these two materials have different band gaps with different lattice constants. So that will form a heterojunction. So modulation doped heterojunction or Schottky structure, that is formed by aluminum gallium arsenide. In modulation doped heterojunction, the left side material, here the left side material, this is actually the material is placed like this is the left side. If you place this material just tilted tilted on left side, so this aluminum gallium arsenide will be coming on the left side, and this gallium arsenide substrate will be coming to the rightmost side, right? So this left side material, that is the gallium arsenide, that's the left side material is the gallium arsenide doped with aluminum gallium arsenide N-type, which is nearly intrinsic, that is lightly doped material, and that is grown over a lightly doped gallium arsenide P-type material, and the whole structure is grown on gallium arsenide substrate which is semi-inflating in nature. So in a gallium arsenide substrate, lightly doped P-type gallium arsenide is the over which the aluminum gallium arsenide is grown. Okay. So the interface between the gallium arsenide and aluminum arsenide will be here. That is the interface. So this is the surface. This is the surface, or this is the interface surface of aluminum gallium arsenide and gallium arsenide. And this is the band diagram. I will explain to you how this band diagram comes and all those things. Okay. An inversion layer of electron is formed in the gallium arsenide close to the gallium arsenide aluminum gallium arsenide interface similar to the MOS structure. In this particular modulation doped heterojunction, an inversion layer of electron is formed in the gallium arsenide aluminum gallium arsenide interface that we have seen the case of MOSFET. The same way, the devices based on aluminum gallium arsenide structures can be used to much higher frequencies than silicon devices. That is the advantage of using aluminum gallium arsenide structures. These structures, aluminum gallium arsenide structures, heterostructure can be used, or such device can be used at higher frequencies than the silicon devices. And this aluminum gallium arsenide structure gives a very high mobility of electrons. That is the mobility of electrons which is due to the mobility of electrons in the gallium arsenide. Why this structure is called a modulation doped heterojunction? This structure is called a modulation doped heterojunction due to the process of modulation doping, because the method to produce it, the method of producing this heterojunction is due to, or is known as, that process is known as modulation doping. Now we have to see what is meant by modulation doping. Modulation doping, of course, we will see what is meant by modulation doping. All those things I think we have already discussed about this one. What is meant by modulation doping? Let us consider the case of this modulation doped heterojunction and how this junction works. We will see a deep aspects of modulation doping and all when we discuss about the modulation doped field effect transistor, MODFET. So we have to study in detail about the construction features and the other band structure diagram and all those things of a MODFET, modulation doped field effect transistor. So first to understand what is meant by modulation doped heterojunction and how this junction behaves. Consider the hypothetical situation of figure A before the two semiconductors enter into contact. I told you two dissimilar semiconductors which comes in contact with each other will form a heterojunction. Before the two semiconductors enter into contact, what is the situation, or what will be the nature of the band structure of the material? In the figure, only the bottom of the conduction band and the Fermi levels are shown, which in the case of n-type aluminum gallium arsenide is close to the conduction band, and for lightly doped gallium arsenide, lightly doped, what type of material? Lightly doped p-type, lightly doped gallium arsenide is located close to the middle of the gap. So let us consider this one. So this is the band structure, or that is the conduction band. This is for the conduction band energy, and this is for the Fermi level, and this is the for the gallium arsenide, this is for the aluminum gallium arsenide. For the aluminum gallium arsenide, actually this conduction band is very close to the Fermi level, and for gallium arsenide, of course, it is nearly on the middle of the middle, isn't it? So here let us consider this one. The Fermi level in the case of gallium arsenide is located close to the middle of the gap, isn't it? So this is the gap between the conduction band and valence band. So the band structure that we can see in the case of this one, the band gap between this conduction band for this one, and this is for the aluminum gallium arsenide, and this is for the gallium arsenide. So this is the band gap energy. That band gap energy, that is delta EC. Okay. So we will see that one. What is the bands are flat because the materials are electrically neutral and have uniform doping. When two materials are not joined together, the bands are flat. Bands, the conduction band for the aluminum gallium arsenide and gallium arsenide, which are flat in nature. There is nothing happening there because both materials are electrically neutral and with uniform doping. The barrier between them in the conduction band, the barrier between them in the conduction band, that is delta Ec. The barrier between them means that is the conduction band, that width of the conduction band for aluminum gallium arsenide and from the gallium arsenide, that gap width is the barrier width between the conduction band and valence band. Conduction band of the two material, not valence band, conduction band of the gallium arsenide and aluminum gallium arsenide. The barrier between the conduction band delta Ec can be approximately found using the Anderson rule. According to this rule, when we join two materials, the vacuum levels should line up. If Xa and Xb are the electron affinities of the aluminum, gallium arsenide and gallium arsenide respectively, then the barrier gap, that is the conduction, barrier between the conduction band, the barrier between them in the conduction band, that is the width of the conduction band for the gallium arsenide and aluminum gallium arsenide, that band gap width, that is barrier width, that is the barrier here, and that barrier width is delta Ec. And if Xa and Fb are the electron affinities of these two materials, aluminum gallium arsenide and gallium arsenide, then delta Ec, that barrier gap between in the conduction band, actually this is the conduction band gap of the two materials, that delta Ec is equal to Xa minus Xb. That is the Xa is the affinity for the affinity of the electrons in the aluminum gallium arsenide, and Xb is the affinity of electrons in the gallium arsenide. The electron affinity of a semiconductor is defined as the energy required for an electron located at the bottom of the conduction band Ec to get out of the solid. So that is what is called the electron affinity. So when we say electron affinity Xa means that is the energy required for an electron, that is the energy to be possessed by an electron located at the bottom of the conduction band to get out of the solid. To get out of the solid means to come to the, that is to come for motion, that is to get out of the solid. Then the figure shows the energy level diagrams for the quantum well formed before the conductors are semiconductors are in contact, and after a heterojunction is formed. So this is the band structure. This is the energy band structure for a heterojunction formed by aluminum gallium arsenide and gallium arsenide. And before contact, this is the band gap of energy of the conduction band for the gallium arsenide and aluminum gallium arsenide. When these two materials are joined together at the interface, of course, the energy of the conduction band, what happens? So here this is the shape of the band diagram for energy for the materials when it is joined together and a heterojunction is formed. The barrier between them in the conduction band, that is delta Ec, that delta Ec is now shown here, see here, and this is for Ec. This is for Ec, that is the conduction band for aluminum, that is gallium arsenide, and this is for Ec4, this is the curve Ec4 aluminum gallium arsenide. Previously it was like this, straight, isn't it? This is straight. Now here for gallium arsenide it is like this. This is the conduction band energy, and for this is actually the band structure for conduction band in the case of aluminum gallium arsenide. Now we see the barrier between them in the conduction band, that is delta Ec, can be found using Anderson rule, and is approximately 0.35 electron volt. Of course, for aluminum gallium arsenide structure, as per Anderson rule, this barrier gap between gallium arsenide and aluminum gallium arsenide, that is the barrier in the conduction band. That gap between them is given by delta Ec. Okay, delta is. So this is the energy band formed at the heterojunction, and here this is the well formed at the interface between the two materials. This is the well formed, and this well is in the shape of a triangle. That is why it's a triangular quantum well with energy E1. This is the energy E1 of the quantum well, or energy at the interface of the quantum well formed is equal to E1. Okay, now we will see how these are all possible. When both materials, aluminum gallium arsenide and gallium arsenide, enter in contact, some of the electrons from the donors of the N material will cross the interface, reaching the undoped gallium arsenide. So, from the lightly doped N material aluminum gallium arsenide, some of the electrons will cross the interface and reaching to the undoped gallium arsenide or intrinsic type of gallium arsenide. So, when the material are in contact, the electrons from the donors of the N-type material of aluminum gallium arsenide will cross the interface and which reaches to the undoped gallium arsenide. Therefore, an internal electric field will be created and directed from a non-neutralized donors in the aluminum gallium arsenide to the additional electronic charges in the gallium arsenide. This electron charges, the crossing of the electrons at the interface from donors of N-type material to the undoped gallium arsenide material causes to produce a electric field between them, and this field is the one that actually causes the band bending shown in figure B. See here, the band is, so here this is the band for the aluminum gallium arsenide, and this is the band, energy band for the gallium arsenide. And this band bending, previously it was flat. Here, when these two materials are joined, the aluminum gallium arsenide, this is slightly, though it is slightly doped, some of the electrons from this aluminum gallium arsenide will be crossing and reaching into the gallium arsenide region through the interface, while crossing it through the interface. And this that electron which crosses from the aluminum gallium arsenide to the gallium arsenide may cause to produce a field between them, between the two material, that between the interface. Okay. And it is due to this field setup that causes the bending shown in figure B. That's the reason why this bending is caused. This bending in the energy band is caused. Okay, due to the electric field setup. Then, at equilibrium, the two Fermi levels line up. The bands are bent like in the case of p-n junction, with the only difference that the barrier delta EC is created. So here at equilibrium means when the system is at equilibrium, when the heterojunction is at equilibrium state, the two Fermi levels will line up and the bands are bent like. It is very similar to a p-n junction with only the exception is that here the barrier in the conduction band, that delta is created between the two material junction. A quantum well for the electrons has been formed, which is limited by a potential well of height delta AC. Actually, this is the reason how the quantum well is formed between the interface of the heterojunctions formed by aluminum gallium arsenide junction with a potential well height of delta EC. With a potential well height of delta EC in the left and a potential energy curve at the right within the gallium arsenide. So here the potential well height delta EC is actually developed here, and at the same time the gallium arsenide potential band, the energy band is bent like this. So that actually, this is the aluminum gallium arsenide N type, this is the gallium arsenide, and here this particular heterojunction, when it is formed, causes to produce an electric field between them due to the crossing of electrons from the N-type material to the undoped gallium arsenide, and that causes to produce an electric field, and that electric field actually causes to have this bending of the two bands. And of course, it is at this interface junction 2D electron gas is formed, that in the form of a triangle. That's why it is called a triangular quantum well. Hope you understand that. Okay. And that potential height of that particular quantum well formed is delta EC. I told you all this. The wells cannot be assumed to be of infinite height, since in our case EC is equal to approximately 0.3 electron volt. I told you already from the Anderson formula. We have already discussed about that. So energy for the motion of electrons along Z is quantized in potential well. So in this case, of course, the energy for the motion of electrons in the Z direction, of course, in a triangular quantum well, it's a two-dimensional quantum well, that is two-dimensional electron gas. So it is actually a quantum well in which two-dimensional motion or the electron motions are actually confined to xy, which are actually confined between x and y directions, and it is confined to z direction. So the one dimensional that is electrons are confined to move, or the motion of electron is in the direction of xy, not in the direction of z. It is confined in the z direction. So this potential, which can be quantized along the z direction, that is, this potential well can be quantized in the z direction. The most important aspect of this heterojunction is that the charge carriers are located in a region, mainly in the gallium arsenide. Not aluminum gallium arsenide, gallium arsenide actually. Charge carriers are actually located in a region that is mainly gallium arsenide, and that is partially separate from the aluminum gallium arsenide semiconductor, which originates the free electrons. That is the mechanism involved here. Actually, the free electron movements are actually originated from the N-type, lightly doped N-type aluminum gallium arsenide. But the charge carriers are mainly located in a region, and the electrons from the N-type material, N-type aluminum gallium arsenide material, crosses this particular interface and reaches at the gallium arsenide. So charge carriers are actually located in a region, mainly in the gallium arsenide, but which are spatially separated from the aluminum gallium arsenide, which are the originators of these free electrons. The electrons in the well should have a very high mobility for their motion along the xy plane. Along the xy plane, these electrons have a very high mobility, since they move within the gallium arsenide, which is free of doped impurities. Because in the xy plane, these electrons can be have a very high motion, or it's a high mobility electrons. And why this high mobility of electrons is possible in the xy plane? Because they actually move within the gallium arsenide, which is free of dopant. The gallium arsenide, which is free of dopant, there is no impurities. So there is no scope for impurity scattering possible. We have already discussed about impurity scattering of the electrons due to the impurities added, isn't it? So here in the case of gallium arsenide, which is free of dopant impurities, and it is well known that impurity scattering is one of the main factors which limit the carrier mobility. So the carrier mobility of the electron movement, or the mobility of the electron carrier, will be decreased or reduced if there is impurity scattering. But in the case of gallium arsenide, of course, there is no dopant impurities in this particular material. That is why impurity scattering is not occurred. Okay, so impurity scattering is not there. Devices based on aluminum gallium arsenide structures can be used to much higher frequencies than silicon devices due to the high mobility of electrons in the gallium arsenide. So electrons are located in the gallium arsenide, where the electron movement is high electron movement is possible in the xy directions. So high mobility of electrons can be done in the case of gallium arsenide region. So this kind of device can be used as a high frequency device because high mobility of electrons is possible in the gallium arsenide. The transistors made with above heterojunctions are called modulation doped field effect transistors. Usually, the MODFET, the modulation doped field effect transistors, are working on this principle, which is essentially called a high electron mobility transistor HEMT. So, it's a high electron mobility. And why high electron mobility is possible? Because in the X-ray plane, high electron mobility is possible because in the aluminum gallium arsenide structure, the electrons are located on the gallium arsenide, which is free of dopant. So, impurity scattering is not possible with gallium arsenide. So, there is no carrier motion limited by impurity scattering. So, high mobility is possible for electrons for this kind of instrument, this kind of devices. So, this kind of device produced by or fabricated by aluminum gallium arsenide structure is essentially a high electron mobility transistor. MOSFET can be used in many high frequency applications due to the very high electron mobility of the electrons in the channel. Now, the lattice constant is the physical dimensions of the smallest repeating unit that passes all the symmetry of the crystal structure. I told you already lattice constant. What is lattice constant? Lattice constant is actually the physical dimensions of the smallest repeating unit that possesses all the symmetry of the crystal. Actually, it is the lattice means lattice structure, that is the crystal structure of the material through which the material solid has been formed. So, that lattice constant is the physical dimension. There will be a physical dimension both suppose if you consider a cube shaped crystal. So, for which there will be length, width and height, isn't it? These are all same in the case of a cube size. So, in that case, we can have these three dimensions as its constants. Apart from that, there will be angular displacement between these three dimensions. So, these six dimensions could be considered as the lattice constant for explaining the crystal structure of such materials. The 3D crystal is considered to have three lattice constant in terms of length of the unit cells edges A, B and C, and three lattice constants in terms of the angle between them alpha, beta and gamma. I just told you now. So, the three in terms of the length of the unit cell, that is a cubic cell, unit cell, which has got three dimensions, isn't it? So, this three lattice constant. Apart from that, there are three more lattice constant possible in terms of the angle between these three unit cell lengths. This set of six constants are termed as lattice parameters and give the entire structure of the lattice. So, for a lattice, these six constants, that is three unit length dimensions along with the angle between these three dimensions. So, likewise, six constants which are termed as the lattice parameters of materials, lattice parameters of the solid materials, which give entire structure of the lattice. So, this is that particular lattice structure. So, here this is this XYZ directions. We have A, B and C. So, A, B, C are three lattice constants and the angle between them alpha, beta and gamma, and that represents six constants for the lattice form. This is the unit cell formed by the unit cell called a lattice structure of a particular material, for which these six parameters can be the lattice parameters. So, with this we complete the session here. So, thank you very much for patiently listening to my lecture session. Wish you all the very best. Thank you.